In this video, we're going to look at questions 15, 16, and 17 from your exam review. Question 15 here focuses on vocabulary that we use when discussing characteristics of different functions. Each of these questions refers to the group of graphs that are shown below on your exam review, and I have those graphs on the next slide. So question A says, which of these graphs represents an even function? Now remember, an even function is when I can substitute in a negative x and the result that I get out is the same function value I get when I substitute in that same x but on the positive side. What that looks like graphically is that we end up with y-axis symmetry. So looking at our graphs down here, that's what we're looking for is y-axis symmetry. And I see we have that here on graph B. Also on graph D, and finally graph G. So B, D, and G would be the answers to this first question. Question B asks us which of the graphs represents an odd function. Now an odd function is whenever we substitute in a negative value for x, we're going to get the same number out, but it's going to be the opposite sign. It's going to be negative. What this looks like graphically is what we called origin symmetry. So let's look at our graphs. We're looking for origin symmetry. And we have that here on graph C. What origin symmetry means is that we have the same thing going on here in quadrant 1 as we have in quadrant 3. Sometimes in class I refer to this as diagonal symmetry, symmetry through the origin. So we have that on C. It looks like we have it again on E, and also here on graph H. So C, E, and H. Next question, we're looking for a graph or graphs that are always decreasing and concave down. So decreasing just means as I read the graph from left to right that the function values are getting smaller. They're going down. Concave down talks about the curvature of the graph, and that means that the graph has a curve that's opening down like this. So let's look at our graphs. Looking for always decreasing and always concave down. This first graph is certainly decreasing always, and the curve is opening down. So this graph meets those two characteristics. On graph B, this graph starts out decreasing and concave down. But then as we go past the 0, we're still concave down, but now it's increasing. And so that one does not meet those qualifications. On graph C, it's not always decreasing. Same with D, same with E, not always decreasing. Nor is it always concave down, actually. Now on F, here we have a graph that is always concave down, but it's increasing, so it doesn't meet both of those qualifications. On G, I want to point out here that this absolute value function, since these lines are straight, it has no concavity at all. And question H, graph H, here we are decreasing and concave down. On this side, we are decreasing again, so this graph is always decreasing, but over here on the positive x side, we are concave up. And so the only graph that meets those two qualifications is graph A. Okay, next up it asks which of the graphs has a relative minimum that is also an absolute minimum. So a relative minimum, remember, is a minimum point in a particular section of the graph. So it may not be the lowest point on the whole graph, but it is the lowest point in a certain part of the graph. An absolute minimum, that's the lowest point on the entire graph. So let's look at our graphs. On graph A, I don't see any minimums at all. On graph B, we've got a, oh, sorry, I forgot to get the, here we go. On graph B, we do have a relative minimum here, and that would also be the absolute minimum, the lowest point on that graph, because it's going to infinity on both sides. On graph C, we do have a relative minimum here, but it's not the absolute minimum because this graph is going to go all the way down to negative infinity. Graph D, this parabola, quadratic, we've got a relative minimum here, and that is going to be the lowest point on the graph. So it's also an absolute minimum. On E, now this graph should have given you probably a little more to see. This is meant to be a sine graph. And so if you imagine the sine graph, it just continues oscillating from -1 to +1. And so this point down here, it is a relative minimum. It's also going to be the lowest point on the graph, the lowest value on the graph. It will keep repeating over and over again, but it's still going to be the lowest. So E qualifies. F, there's no minimums at all. G only has a maximum. And H has neither relative minimums nor maximums. So it looks like for this one we've got B, D, and E. All right, next up, which of the graphs has an inflection point at x equals 0? Now, an inflection point is a place where concavity changes, where we switch from concave up to concave down, or from concave down to concave up. So let's look at our graphs. Graph A, I don't have any change in concavity. Same for graph B, it's concave down on both sides. Graph C, notice it's concave up and then concave down, and right here at x equals 0, that's where the concavity is changing. That's the inflection point, and so C is true. D, I don't have a concavity change. E, again, changing from concave up to concave down, right there at the origin. F is always concave down. G has no concavity. And H, it does change from concave down to concave up, but there's no inflection point there at x equals 0 because on that graph we've got a vertical asymptote there. So my only answers to this question are C and E. Our last question here says, which of the graphs changes concavity but does not have an inflection point? And we just talked about that as we were working through. That's going to be that graph H. All right, let's move on to question 16, where it talks about the domain, asks us to find the domain of the following functions. So for this question, we need to remember from our parent functions what the domain restrictions are. And there's only really 3 types of functions that have domain restrictions. Those are rational functions, square root functions, and log functions. And so we've got one example of each of those here. For the first one, we've got a rational function. And when we're dealing with rationals, we need to see that this is a fraction. It represents a division that's happening. And the main rule to keep in mind here is that you can't divide by 0. Our denominator cannot be equal to 0. So x squared minus 4 cannot equal 0. And if I factor that, I get x plus 2, x minus 2. And so this means that x cannot equal -2 or 2. And so if we were going to write out a domain, this would be all real numbers, x not equal to -2 or 2. Now for a square root function, whenever we are taking the square root of values, those values have to be positive or 0. We can square root 0, we can square root positive numbers, we cannot square root negative numbers because then we get an imaginary value. And so that means that what's under my square root here, 2x minus 5, it has to be greater than or equal to 0. And then all we need to do is isolate the x. So 2x greater than or equal to 5, and x greater than or equal to 5 over 2. And so that would be our domain for that particular function. For the last one here, we've got a log function. And with logs, we can only log positive values. You cannot take the log of a negative value. You cannot take the log of 0. And so this one is going to be similar to our square root example, in that we're going to write 4x plus 7 greater than 0, but we're not going to include the or equal to, because you cannot take the log of 0. I'm going to isolate the x. 4x is greater than negative 7, and then dividing by 4, x is greater than negative 7 over 4. And that would be our domain for this function. All right, the last question for this video is just asking you to sketch some graphs of parent functions with simple transformations. And you are being asked to do this without your calculator. We should know what our parent function graphs look like. We should also be able to apply these transformations. So let's start with question A. I see that I've got a quadratic function here. And my transformation is that the parent function is being moved to the right 3 units. So 1, 2, 3, and a quadratic graph. All right, question B. E to the x, and we've got a negative in front. That negative in front of the whole function, that's going to reflect the function over the x-axis. So my exponential graph flipped over the x-axis. That graph should look something like this. Next, question C. I've got an absolute value function here. It's being shifted down 1. Also, I've got a vertical stretch of 2. So absolute value, I'm going to go down to negative 1, and then we're going to stretch it There we go. Vertical stretch makes that graph a little bit skinnier, makes the slope steeper, shifted down to negative 1. All right, D, sine x plus 2. So we've got the parent function of sine with a vertical shift of 2. Normally, sine oscillates around the x-axis. The midline is the x-axis. We're going to move that up to 2. And then my sine graph, it starts in the middle. And should look something like that. Next up, we've got a cubic graph, cubic function, and I've got 2 transformations here. First of all, the negative here in front, which is going to flip the graph over the x-axis. The minus 2, that's going to move our graph down 2 units. So my inflection point is going to be down here at negative 2 instead of at the origin, and my graph is going to be decreasing instead of increasing like the parent function. Last one, natural log of negative x. So the transformation that we have here is a negative, and this is on the x, it's not on the entire function, and so this is going to reflect our parent graph over the y-axis. So if you think about that parent graph for natural log, and we're going to flip it over the y-axis, and so it would look like this.